Good morning, everybody. Today we're going to be working on Lab 4 for R. And in this lab, we're going to discuss a little bit about how R handles distributions. We're going to talk about the same three distributions that we talked about in class, the binomial, the Poisson, and the normal distribution. Okay, so again, in this case, Google is your friend. I'll show you some basics in terms of like how we use the P norm, Q norm, and all that stuff. But you can expand it as much as you want. And there's a very nice documentation for all of the functions that I'm going to put here. The first example that I want to talk about is starting with a binomial distribution, create, let's say, starting with a Poisson distribution, a Bernoulli distribution, create the corresponding binomial distribution, and utilize it to answer some questions. So in class, we talked about the Milgram's experiment. Remember, this is a set of repeated Bernoullis, right? The probability of success is always fixed. Let's call it lowercase p. And what you're asking is, what is the number of successes in a certain set of trials? But I have a little bit more than that. So the first example says that we have n trials. So we have 20 trials, so n equals 20. And the probability of success is p equals 0.35. So we're kind of repeating the Milgram's experiment with 20 participants. The first question is, what is the probability of 10 or fewer successes? So smaller or equal to 10. Then what is the probability of 9 successes or fewer? Again, smaller or equal to 9. Then what is the probability for exactly 10? So probability of x equals 10, strictly greater than 10, and then finally between 8 and 10, right? And in all these situations, what we're using is some sort of like the probability density function and the cumulative probability density function. And R has, equations for both. So the cumulative probability function in binomial is denoted by this P binom, right? And we decided to use this capital letter F to denote that, and then leave lowercase f for something else. So if I want to find what's the probability of up to 10, including 10, I have to use this line of code. The P binom, I need to tell it how many I want. So 10 in this case, I need to give it the size, basically the n equals 20, and what is the probability of the success. So if you grab this line here and you drop it into the little R code, which I'm going to bring up here, and go ahead and create a new one. So save as, and I'm going to go and put it, let's leave it in this folder here. So let's go to general labs, lab new, and I already have a lab 4 here. I'm going to go into R. I'm just going to name this one Lab04, I guess, codes. All right. And so the first thing you need to do is basically just drop this line here. And what this is going to do is it's going to use the function P binom, which is inside, the basic R. So you don't need any packages for that. And save the output as F10, right? So when I run this, you'll have this property here, F10. If you want to see it in your console, you just need to type F10, right? Once again, here we denote F10, so it saves it in. If you want to see it, just run this line. You'll see down it's 0.9468334. Okay, so relatively high probability. So then the second question that we have is smaller or equal to 9, and it's again the same thing. The thing that you change is from q equals 10, you do q equals 9. All right, now let's call this F9. And again, as the P binom, if I run this, it gets saved up there, and you can view it by just typing F_9. Okay, so there we go. I like to use underscores instead of anything else. We shouldn't use parentheses because parentheses is a symbol inside R, so underscore is pretty good. Okay, so that's 0.87. And then to answer the next question, it said exactly 10. Now, if we think about it for a second, that is the probability all the way up to 10 minus the probability of all the way up to 9, right? Because whatever is left is the probability of 10 exactly, right? So what we need to do is literally subtract the two probabilities that we just computed, right? So you're finding the probability up to 10, you find the probability up to 9, and then take the difference. And that's how you deal with discrete distributions. We'll see how you deal with it with continuous distributions. But if you're looking at the discrete value at a fixed point, the best way to do it is find the cumulative probability up to that point and subtract the cumulative probability of the point right before that. Okay, so remember this little trick. With symbols, we're working on this. With functions, we're just running the difference. And we'll computing the difference, and I'll just denote it by F10 minus F9. If you have computed already some properties and saved them there, then you can use them basically to create a new property. Remember, R can function as a big calculator. All right. So that's P of 10. Now, there's a different way to do it, and I'll show you this here. There is a straightforward way to do it by using the function dBinom. So if I use this one and compute F of 10 with a dBinom and run it, I'm again going to get the same value here, right? It's 0.068. So two ways of finding it, either with the difference of the cumulatives or just with a dBinom. All right. And notice again, the syntax, you just say at which point, what is going to be the total size and the probability of success. All right. So two ways for you to figure this one out. I like to put this over there because that gives you an idea of how we find generally probabilities of certain sets. Now, let's continue on and try to figure out now how to find the probability of being greater than 10. And as a matter of fact, there is no built-in function to find you this probability, right? So the built-in functions in R find the probability up to something. And notice here that you want from that, you know, all the way up to 20. So what you do in these cases, you start to think, I know some facts. I know that the probability of small or equal to 10 and the probability of strictly greater than 10 are complementary events, right? So if I find the probability of small or equal to 10, I can just subtract it from 1 and get exactly what I want. So the immediate way to do it is this one with the FC10. I like to use FC. Remember, it's the complement. Okay, so by this definition, I'm talking about F10 is the cumulative probability up to 10, including it. And so if I throw in a C, I mean the rest. So you can again use some sort of computation. Remember, you can either use F10 or whatever is equal is. So if I run this line, you're going to get basically 1 minus that. Now, I could have just used only this, right? Because I've already computed it, and you're still going to get the same number, right? I have an extra parentheses. There we go. Okay, and you get exactly the same number. All right. Now, if we're looking at specifically these discrete probabilities, there is a way, a built-in function to do it, but you have to tweak a little bit the argument. It's again the p-binom, and what you need to do is you need to add this lower equal false, right? So what does that mean? Well, by default, right, we're looking at the lower values, 10 and lower. So if you do lower equal false, it means don't look at that. And the only thing that you're left with is 10 and above. All right. So if you run this line, you get exactly the same value. Okay. So that's another way to do it. And yeah, I said in the beginning, there is no real default way. I mean, in general, like for the binomial, there is. And for many other ones, there is. But for some crazy ones, there might not be. The easy one would be like find probability up to that, which always exists, right? If you have a distribution in R, you always have some sort of cumulative distribution up to something like that. Okay, but p-binom, here's another way to do it. All right. Now, the last part is, remember, we want to find something between two numbers, so between 8 and 10, including both of them. And here's where we need to use a little bit the math and the formulas to understand exactly which values we need. So the probability between 8 and 10, including 8, is the probability up to 10, including it, minus the probability of everything up to 8, excluding 8. Right? So we want 8 to be in that calculation. So excluding 8 means strictly smaller than 8. So that can be the same as smaller or equal to 7. Right? So the probability from 8 to 10 inclusive 8 is actually the cumulative probability up to 10 minus the cumulative probability up to 7. So Again, there's a gentle, discussion that needs to happen here and some sort of computation that needs to happen in your head. But basically, this probability is the cumulative distribution up to 10 minus the cumulative distribution up to 7, right? And that's the only thing that might trip you up. So I call this P of 8, 10. And again, I'm using the P binomial. And as you can see, up to 10 minus up to 7. So there's a fast way to do it. And there it is. Oops, no, I don't want that. I want the next line. So let's copy this and put it here. All right. So P binomial up to 10, P binomial up to 7, because we want 8 to be included there. And you get a value of 0.345. All right. Once again, you can just run this and see the value down in your console. Okay. Now, there is another way to do it again, right? You can find the actual probabilities for 8, 9, and 10 and add them together, right? Because what is the probability between 8 and 10 in the discrete binomial? Is the probability of 8 plus the probability of 9 plus the probability of 10. So we could again use this computation that finds the specific probabilities for 8, 9, and 10, then adds them all together. And you can either put them in steps or you can put it all together. Various ways to get to the same answer, as you can see down there, right? If I run it, that's the same answer. Boom, there we go. Okay, so many ways to do that. It's just that I think this type of computation is going to work for any sort of probability distribution that you see in R. Okay, so let's go ahead now and figure out the second part of this lab. And here we're going to work a little bit with the Poisson distribution. And remember, the Poisson distribution is some sort of like abstraction of the binomial. You still have successes and failures, but there are infinitely many. And in class, we discussed that this is the formula of k occurrences when the average is given and it's a small number. The corresponding function now is P Poisson, D Poisson, and so on and so forth. Let's suppose that we anticipate one traffic accident on I-10 every morning. Okay, I'm just keeping this simple. I think now the average is something like 3 or 4 per day or something weird like that. But anyway, let's assume that there's one traffic accident every morning on I-10. What is the probability that up to 3 accidents happen tomorrow morning? And if you read up to 3, that basically means 3 inclusive, right? So the probability from x smaller or equal to 3, and that includes, 0 accidents, which we tend to forget, 1 accident, 2 accidents, or 3 accidents, right? So basically, we're trying to find the cumulative Poisson distribution up to 3, and that is very easy to implement in R. It's a P Poisson computation. And so you just put F3 P Poisson, just to remember that we're now switched to a different distribution where we're using the binomial up here, and we're using the Poisson down there. And by the way, this P, D, and all that is pretty common. So everybody that creates a distribution tends to use similar letters, but it might not have all the bells and whistles, for example, that the binomial have. In any case, what you need to show is like how many do you expect, right? Up to, and then what is that lambda, right? Remember, that was the average on a fixed interval. So if we run it, you get an F3. If we select one and see it, this is at 0.98. So there's like practically 100% chance to see an accident, as to see up to 3 accidents. All right. So you can see 0, 1, 2, and 3. Now, if we want to compute the probability that you see more than 3 accidents, right, we need to remember, again, the complement, right? So greater than 3 means 1 minus smaller or equal to 3, the probability of smaller or equal to 3. So just 1 minus what we computed before. And I can compute it again like this, or I can invoke the F3 that I've already created, right? But let's go ahead and do it like that. Again, notice the FC here, very easy to remember stuff. And it turns out to be a very, very small number. I don't know. I need to update this homework a little bit because, yeah, it seems to me that we do see a lot of accidents on I-10 every morning. But anyway, based on this computation in this model, the probability is like close to 2% or something. Okay. And that's how you handle that. We could, again, look at some of other ways of doing it, like doing some sort of probabilities here for 4, 5, 6, and so on and so forth, and start adding them together. We will notice that pretty soon that kind of stabilizes on the same number. But it's impossible to just do it all the way, right? Because you need to add 8, 7, 8, and so on. Of course, after 7 or something, the probabilities are super small. So you'll see that this number gets very, very close to that. But I would avoid this part. I would stick with this cumulative distributions. This is just to show you that, if you could theoretically repeat this infinitely many times, all these strings together would end up with this number up here. Right? Now, the last example that I want to talk about is the normal distribution. And, we're going to be working with normal distribution a lot. So let's figure out how to use it here. And by the way, it's one of these distributions that definitely pop up in your research too, every now and then. So might as well learn as much as we can about it. The example that I have in this lab has to do with IQ scores, a very controversial number. I don't put much faith to it. I used to put a lot more faith to it, but I've read a lot of the literature, and the IQ score is, well, although scientifically sound, it's not representing exactly what we think it is representing. And anyway, it's good for an example now. And what is the IQ score? It's basically like there's also a standardized test that people take. It happens in practically all countries in the world. And that test, changes every year. It supposedly measures your aptitude to solve, tasks that have to do with, how smart you are. And it is designed in such a way so that the average person scores 100, right? And then there is more or less a fixed standard deviation. Remember, when you're talking about a normal distribution, you need to supply the mean and the standard deviation. And in the United States, last time I checked, the standard deviation was 15 points. That is also like what the global tests are trying to achieve, but it's not like a hard requirement. The mean equals 100 is a hard requirement. So anyway, it is designed in such a way so that the average person scores 100 in this. And so let's assume that the normal IQ score for the United States is normally distributed with a mean of 100 and standard deviation of 15. So the corresponding graph is like that. Now, the coloring here is very, very suggestive, and we'll see what that means. I also put an image for the source here that has a lot more information about the IQ. So let's assume that we want to find the probability that you're between 85 and 115, that your score is basically somewhere in between, including both ends. So actually, no, including the top end and no, it's actually the whole thing. All right. So this is the probability of up to 115 and below 85. Remember that we're now talking about a continuous distribution. So putting here equal or not equal, doesn't change things much, right? And we'll see that again back in class. So anyway, we're trying to find what's the probability a person is between 85 and 115. We can use this P norm with, again, providing the mean and the standard deviation. And if we plug that into our, we will get this number. All right, so if I run it, it is 0.68 and some change. So basically, this is the probability of landing within one standard deviation from the mean. All right, so we are 68% of people, land within one standard deviation away from the mean if we're working with an IQ test. All right. Let's extend it. All right. So that's this green piece here. So in a sense, the area of this curve is 68% of the total area. All right. Now, let's look at what happens from 70 to 130. Again, you can use this P norm computation and the differences. And when you plug it here, what you get is, run this and select this one to see it. This turns out to be 0.95. So 95% and some change again. And basically, this is the area from here to 130, right? So from 70 to 130. So within 2 standard deviations, you have more than 95% of the probability. And so if we're working with a normal distribution, right, 95% of people land somewhere between 1 and 2 standard deviations. And that, plus or minus 2 standard deviations from the mean. And that is the reason in the beginning of the class when I said the one way to detect outliers would be to set it to be 2 standard deviations away from the mean. We borrow that 2 standard deviations away from the mean because that's how it works in the normal distribution, right? So in the normal distribution, practically everybody, 95%, is within 2 standard deviations from the mean. And then outside that, there's just like the 5% or something, okay? And that can be considered like an outlier, okay? So that 5% is also very useful. Later on, we're going to be doing hypothesis testing. So that 5% for us is like this magical bound that we say, okay, we allow 5% of outliers, and we focus on the 95% that seems, normal. Okay, so that is in the normal distribution, that is within 2 standard deviations. That's why we extend that definition to like practically all, the distributions that come from data. Okay, so assume now that you have a person that scored 132 in an IQ test. Let's try to find what is the probability to get that number and above. Remember, we can't just find what's the probability of 132. We're going to get 0, but we can find that probability and above. So what is the probability a person can get more than 132 on a standardized IQ test? And if we run this, we can do it 2 ways, either again by subtracting from the probability up to 132, and that's going to give us, let's run this, 0.016. Again, I found the probability up to 132 with this, and I subtracted from 1. Or we can do it with the lower equals false, and we will get the exact same number. So basically, the probability of a person getting 132 and above is like 1.5% or 0.016. Okay. So very, very low, but definitely doable. And that is the score that you need to have in order to be a part of Mensa. And that's an international organization, for very smart people, whatever. I have some information over there. If you feel like taking an IQ test, just know that it's not exactly what it's supposed to be, but some companies are required, some fraternities even could require it. It's a concept that kind of exists and might be useful for some situations. All right. Anyhow, going back to statistics, using these variances of p norm, d norm, and all that stuff, you could compute a lot of things. And these are not the only 3 distributions that exist in R. There are many, many distributions in R. All of them have a similar structure. And once again, if you have a different distribution, Google is your friend, right? Just put, the type of the distribution you're working with and just put R implementation, okay? I would advise you also when you're trying to find specific probabilities to use those letters, right? P, F, whatever. Keeps things tidy, keeps things clean, right? Okay, that's all for today. And I'll see you next time.